All right, we're at 28.5, section 28.5, torque on a current loop in a uniform magnetic field. Let's share the PowerPoint, and the image in the left-hand side is actually taken from exercise 28.4. I encourage you to, I'm sorry, I said exercise, the example 28.4. I encourage you to look that over 28.4. And if you look, you've got a current in this semicircular loop in a magnetic field. So in the straight portion of the loop, you have the magnetic field, you have the current in this direction. So you have the force coming out of the page. In the semicircular loop, you have the magnetic field and you have a current that's in general to the left, so the force is into the page. So you've got on the straight portion, you've got a current, you've got a force out of the page and a force into the page from the semicircular portion. And if you look at the example, they're equal but opposite in direction. So the sum of the forces equals 0. However, if you were to have this mounted such that it could pivot. If you mount it at the extremes of the x-axis, you would form a torque on the semicircular portion of the loop. So just because they are the sum of the forces equals 0, the sum of the torques doesn't necessarily equal 0, and we're going to look at that in this next figure to the right over here. You have a magnetic field and you have this loop going around, and there's 4 sides, 1, 2, 3, 4, and in 1 and 3 there is no force on the current in those wires. Why? Because the sine of theta in that case is 0. There's 0 degrees between the B field and the current, so the sine of 0 is equal to 0. However, in 2 and 4, you're not. That's 90 degrees. So you have the magnetic field and you have the current, and that the sine of 90 is 1, and so you're going to get maximum force. Now let's look at the force. You have. Let's do it this way. You have the magnetic field. You have the current going down. So the on 2, if a force is coming out of the page. In 4, you have the magnetic field, you have the current, so the force is into the page, into the page. So if you look at below this loop, which they're doing here, you can tell that by, you can see this little dot. That means that is coming towards you, and the X means it's going away from you, and you can see that there's a force 2 going upward and a force 4 going downward. Now, let's, so the force 2 is equal to the force 4, and it's equal to IAB. Where do we get the IAB? Well, if you recall, it was I times L cross B. So that's IL B theta, ILB sine of theta. Well, since theta is equal to 1, you just get ILB, or in this case IAB, because the length is this section here, IAB. Oops. So when you have a torque, if you recall, torque is equal to the torque is equal to the force times the moment arm times sine of theta. So here the moment arm is, since it's pivoting at the midpoint of B, the moment arm is B over 2. So we have F2 times B over 2 plus F4 times B over 2. And since F2 equals F4 equals IAB, it's IAB times B over 2. Now, of course, we're talking about uppercase B being the magnetic field, lowercase b being the length of this side over here, which B over 2 is the moment arm. So it's IAB B over 2 plus IAB B over 2. And so it's just IAB. Um, so the torque is equal to IAB, where A is the area of A times B. Little a times little b gives you the capital A, which is the area. So the torque is equal to I times the area times the magnetic field. Now, I'm going to take a break here. In fact, I think I'll stop the share so that you can see this in a on a bigger screen. We're gonna discuss a loop, and if this is a loop, we're gonna learn what the normal to the loop is, and the normal to the loop is a vector going through the center. Uh, that is normal to the loop. Now, if you have a current, going through the, uh, if you have a current going through the loop, the you point your fingers in the direction of the current, and the normal is, I mean, the normal can be in either direction, but we're going to define a vector that is is pointing in the direction of your thumb. As the current is going this way, we're going to define a vector going this way, and we'll see that. But you have to remember that the normal to the loop is the vector that is normal to the plane of the loop. You have to differentiate between, when they talk about a magnetic field, and the angle between the magnetic field and the normal uh, to the loop. It's not the magnetic field. It's not the magnetic field and the angle of the loop. It's the normal to the loop. Try to remember that. Let's go back to the share, and you see that A there is the vector I'm talking about, and you can see that it's normal to the loop. Okay, so let's see. Uh, Here you have uh, what we saw in the previous. This is when the angle is 90 degrees. Now, let's say the angle is not quite 90 degrees. You have the B field here, and you have the normal here. There's theta. When the normal to the loop makes an angle theta with the magnetic field, the moment arm for the torque is B over 2 sine theta. So the torque is equal to F2B over 2 sine theta plus F2B over 2 sine theta. Well, what is F? F is IAB. So it's bottom line is just like last time. It's IAB big B sine theta, capital B sine theta. So that's just IAB sine theta, where A is the capital A, and it's the area of the loop, also represented by this as a vector as this A here. And they're showing you here. Let me catch up to my notes so I don't forget that what the mu is called is we're not there yet, but we're going to introduce a mu that's the magnetic dipole moment, or just the magnetic moment. But here you see we have, if you curl your fingers in the direction of the current around the loop, your thumb points in the direction of A and mu. And mu is a vector called the magnetic dipole moment, or just the magnetic moment. And what is mu? We'll see that mu is equal to I times the area. So the torque is equal to I times A cross B, where A is that normal vector. Mu, the magnetic dipole moment, is equal to I times A. So we can, the mu of the coil is N, the number of turns, times IA. So the torque is equal to mu cross B. And the torque is also the electric dipole moment times the electric field. The little p vector there is the electric dipole moment times the electric field. That'll also give you the torque. Okay, so U of B, the the lowest energy, or the energy, is the negative of the magnetic dipole moment times the magnetic field. Um, okay, now let's take a quick quiz. Rank the magnitudes of the torques acting on the rectangular loops A, B, and C, shown edge on in the figure from highest to lowest. And we can see that um, we want to look at you remember what I said about the normal. So the normal in in the normal here is a oh, I accidentally um, clicked on the answer, but the normal here is in line with magnetic field. So the uh, the sine of 0 is equal to 0. Here it's at 45, so that's 0.707, and here it's 90, so that's 1. So the ranking is actually reverse of what they show here. It's C, B, and A, and there we have it, C, B, and A, because the norm, we have to take into consideration the normal to the loop. Okay, rank the magnitudes of the net forces acting on the rectangular loops. The magnitudes of the net force acting on the rectangular loop shown in the figure from highest to lowest. Uh, the uh, Now pay attention to the question here. Rank the magnitudes of the net forces acting on the rectangular loops. The force is not asking for torque. It's asking for the net forces. The net force in each case is 0 because they're equal and opposite in direction. Now, if it asks for torque, that would be a different story. So it's A equals B equals C. Why? Because the forces are equal and in opposite in direction. And then we're going to end there, and then we're going to talk about the Hall effect, and we'll be done with chapter 28.